What I want to do here is show you some examples of graphs of motion, look at the position, velocity, acceleration graphs using some of the data collecting equipment you guys have used in class. So all I have is the spark that's plugged into a motion sensor, and that's attached to the computer here with SparkView. All I'm going to really do is take an object and toss it up and down, and I'm going to put that right over top of the motion sensor, and we'll show you what type of graph appears from that. So we're going to take the iPad here and just toss it up and down. So if I stretch this data out, what I can see is a very nice parabola. We can tell when the object went up into the air. We can tell when the object started to come back down. So another thing we can do is we can switch the axes here and show that this upwards parabola translates into this velocity graph. So the velocity is a function of time here. So as you can see here, I've got this upward tick in the velocity. That's me throwing the iPad into the air. So it started off around 1.5 meters per second. It quickly came to rest and then accelerated back down towards my hands. This tick right here is me catching it, taking it from downward velocity. It had 2.0 when I caught it. If we take the slope of this downward line, it's going to give me a negative acceleration. And if we look at that negative acceleration, there was an upward acceleration to get the iPad into the air. Then during the free fall, the acceleration was hovering right around 9.5, 9.8. And then that upward again is me catching the iPad. So in one of the WebAssign questions, it has a speeder going past a cop, and the cop needs to catch up to the speeder to pull him over and give him a ticket. The way that you can graphically represent this scenario is a steady line for the speeder. So that shows they're going the same distance every single second. It is a steep slope, which means they're going too fast. But in red, what I'll do is I'll show what the position time graph would look like for the cop. The cop would start out at rest and eventually catch up to the speeder as they accelerate. At this intersection point right here, we know that that's when both the speeder and the cop have caught up to each other. If I would put this onto a velocity graph, we would see two different motions. For the velocity graph, the speeder would be moving at a nice steady speed the entire time, covering the same ground every single second. And the cop would be starting from rest, picking up speed, and eventually reaching a speed much greater than the speeder. We can tell that the area under the graph for the red line tells me how far the speeder has traveled. And if you match that to the area for the blue line, this area down here, this area represents the distance traveled by the speeder. So the speeder traveled that rectangular distance while the cop traveled that triangular distance. But if you look at those two distances, they will both match up in the end because the cop and speeder, so this area and this area, match up. So move that triangle down there, I would get the same exact area for both objects. One was accelerating and one was constant speed based off the velocity graph.